Okay, let's get started. So hi everyone, I'm Bowen. For those who don't know me, I'm leading the teams that work on mostly protocol development. And yeah, today I'll be talking about the work that we have been doing and also some of the future works that we'll be working on. So yeah, let's get started. So yeah, just an overview of what we do. So our goal is to build infrastructure that powers developers to build decentralized applications. And it is intentional that in this phrasing that I didn't put the word blockchain in, because our goal is not to build some sort of blockchain in a vacuum, or even to build it to satisfy some abstract goals. Rather, our goal is to make this such that we can serve the needs of the developers and truly, be aligned with the vision of NEAR. So that means today we're building a sharded proof of stake blockchain, but if in the future there's some change to the technology, for example, some zero knowledge proof technology become mature enough that we can use it to replace some of the things that we have today, we'll be happy to do that. And yeah, just a brief overview of the entire development process. We started back in August of 2018. Back then, I think we started prototyping in Python. We spent a couple months doing that. But then, yeah, actually, I think that was not the most, the best use of our time. And we actually went on to pursue a completely different path. And then we launched mainnet phase 0 in April 2020. This was a proof of authority mainnet that only has validators run by the NEAR Foundation. And then gradually we start introducing more validators from the community. And eventually around, on October 13th, 2020, the vote for mainnet phase 2 happened. Essentially, that was a vote by the community to turn on phase 2, which essentially means that transfers are enabled on the network. So by now, mainnet has been running for about, I think, 8 months now. And it has one shard. And I think, yeah, if you have seen Fro's post yesterday, we produced more than 40 million blocks on mainnet already, and that's that's a great achievement. So before we actually talk about some of the details of work that we do, I just first want to mention the overall priorities for the teams, because this would also be linked to the actual work that we do, as we will see later. So the first priority is, of course, safety and stability of the network, because if the network is malfunctioning or has some critical vulnerability that is exploited, or the network is stalled or like kind of shut down, or someone attacks the network and steal like a ton of money, then obviously that's extremely bad for everyone who's using the network. It will not only cause applications to stop working, but also people would lose trust in us. So our top priority is the safety and stability of the protocol. And then the second priority is to make sure that developers can easily build on us, because after all, we are a developer-focused platform, and we want to serve their needs, and we want to make it easier for them to build whatever application they want to build. And the priority after that is performance and the scalability. So this also ties somewhat into the developer friendliness, because after all, the problem with Ethereum today, for example, is that they have such low throughput that makes it very painful for developer to build applications, and makes it very expensive for them to run any applications. So we will also be focusing on making sure that our network is performant and also has good scalability, so that this will not be a bottleneck in the future. And finally, we also want our blockchain clients, blockchain nodes, to be runnable, meaning that whoever wants to run a node, whether it's validator, whether it's RPC providers, or some other partners, or developers, for example, they would have no trouble doing that. Okay, let's actually talk about the protocol itself. So roughly on the kind of high level, there are 3 components to it. So the first component is this peer-to-peer network. And our focus there is to build a reliable and scalable peer-to-peer network that powers communication between blockchain nodes. So essentially, this is a custom-built protocol that enables communication between blockchain nodes. This includes message routing and things that we will talk later about. But there is essentially no good existing solution for this problem. And then there's chain, which is this, you can think of this data structure that orchestrates everything on the blockchain. So this includes how consensus works. This also includes how sharding works on the high level, meaning like how blocks and chunks, which are shard blocks, are produced and distributed. And then there's also Runtime, which is this execution engine that's basically applies blocks, does state transition, and so on. So yeah, let's actually go into each of the components and discuss in more detail what we do there. So yeah, as I said about the network, is a peer-to-peer communication protocol, and since it's purely peer-to-peer, it means there's no centralized entity controlling how the nodes interact with each other. They essentially follow some kind of custom protocol on how they establish connections to each other, how they send messages to each other, what the format of messages are, so on and so forth. So every node has a unique key that identifies themselves on the network. Now, so the interesting part is that we want to build in such a way that we can route messages from nodes A to node B in a kind of efficient and also resilient manner. So let's actually talk more about that. So in general, in terms of like routing on the network, there's 2 types of routing algorithms. One is called link state-based routing, and another one called distant vector-based routing. The difference is mostly lies in whether the client or the node stores all the information about the network, or only stores information about its neighbors. So essentially, what we do is that each node kind of maintains its own view of the network, and then when for example, when a new node joins, it receives that view from other nodes, and then when the topology of the network changes, for example, when 2 nodes start connecting to each other, or some node disconnected from the network, that essentially means that a new edge is added to the graph, or an edge is removed from the graph. And then that is essentially broadcasted to the entire network by this gossiping protocol. Essentially, like a node will send this message to its neighbors, and its neighbors will send to their neighbors, and then then everyone essentially updates their view of the network.
Well, sorry for interrupting. Can you just check the participants room, because some people say they're waiting?
Oh, okay, sorry about that. Yeah. How do I? Okay. Okay, so sorry about that. Okay, I think I've admitted all of them. Yeah, for people who just joined, I'm sorry. I didn't check the notification there. Okay, so let's continue. So I guess I was talking about how messages are sent through the network. Essentially, once we establish this this entire process, every node would have a view of the network, and then it would know, for example, if it wants to send some message to some specific node in the network, how it should be sent. Essentially, because the network can grow very large, every node does not necessarily have a direct connection to every other node. It will choose a route to send this message through other nodes. And because the node maintains the view of the network, it can choose a shortest path to the destination, and that is exactly what we do. So now let's talk about some of the challenges and the future work that we will be doing in terms of the peer-to-peer network. So first of all, we want to make sure that this peer-to-peer network that we build is safe and is robust. It means that we need to prevent malicious attackers from finding ways to cause other nodes in the network to malfunction. This means that the attacker should not be able to create some kind of attack such that the node would crash because, for example, they run out of memory because the attacker sent them some very large message, or the attacker somehow tries to split the network into half such that the two halves cannot communicate with each other for some reason. And then, of course, we want the network to be scalable as well. That means what we have today, which is maintaining a view of the entire network, it doesn't actually scale very well when there's a very large network. Let's say there's a million nodes in the network, then maintaining an entire view of the network becomes less feasible. So one of the directions we're working towards is to design new ways for nodes to maintain kind of local view or some information locally about the network, and then route messages based on that. And then, yeah, that kind of is an ongoing work. Also, in terms of performance, the current routing algorithm doesn't really take latency into consideration. It essentially route based on the shortest path in terms of the number of hops it needs to take, but it doesn't actually distinguish those different paths in terms of the latency that's incurred by sending messages through that route. So another thing that we can, so today every node has kind of a fixed number of connections to other nodes, and that number is actually quite small. So we are also thinking about doing some optimization there to enable more connections, more direct connections to reduce latency. Yeah, so that's pretty much everything about network. So let's now move on to chain. So yeah, for chain, I'm mostly just going to give a very brief overview of consensus and sharding. So each of those topics can require entire presentation on its own. So I will not delve too much into the details here, and I will just try to give a very high level overview of what we do and how it kind of works. So yeah, the consensus is called Doomslug for people who are familiar with Brandon Sanderson's work, fiction Skyward. Doomslug is this creature. Well, there's actually a picture here that is, well, without giving any spoilers, it is very fast. So that's why we picked the name. Oh, that's why Alex picked the name. So Doomslug essentially is this block production and the finality gadget. And without describing in detail how it works, we can talk about some kind of the property that it has. Essentially, blocks require 2/3 of approvals from other block producers to be produced. And then, yeah, if there are essentially 3 consecutive blocks with 3 consecutive heights building on top of each other, then that would finalize the first block. And also, final blocks cannot be reverted unless more than 1/3 of the state concludes. So that is kind of the Euro BFT stuff. Okay, so Yeah, so similarly, the sharding design is called Nightshade, and yeah, Nightshade is the main character in Skyward. There's some very interesting interaction between Nightshade and Doomslug in the book. So yeah, for people who are interested, can read the book Skyward. So the kind of one interesting design choice that we made in Nightshade that's somewhat different from some of the other blockchains, including the original Ethereum 2.0 design, is that we only maintain essentially one chain, and for all the shards, essentially they only have shard blocks, and the blocks are kind of shard blocks are which we call chunks are actually contained in the blocks on the main chain. So this kind of simplifies things a lot, meaning that we don't have to maintain separate shard chains and have to think about, when there are forks on the shard chain, how do we deal with cross-shard transaction? Because you can have transaction from one fork of one shard to another fork of another shard, and then when that kind of changes, it leads to a bunch of problems, including like atomicity failure and things like this. So essentially, we simplified things a lot by only maintaining one chain, and then the blocks on the chain would include chunks from different shards. And then chunks are distributed to block producers through erasure coding. Well, without actually explaining too much in detail how what that is, it essentially means that it allows us to reconstruct the chunk with only a fraction of the block producers. So we choose the number. So I think in the paper it chooses 1/6, and as here in the actual implementation we use 1/3. So essentially 1/3 of the block producer, or any 1/3 of the block producer, can reconstruct the any given chunk by having the erasure coded part. And then block producers would send approvals once they receive and process block to attest to the validity of the block and also the datability of the block, meaning that they have received their parts for the chunks included in the block. Yeah. So that's kind of a very short overview of how a chain works. So some of the future work are things that we're actively working on, including moving from one shard to multiple shards. So when we first launched mainnet, we didn't, at the time there's essentially no usage, and it doesn't make a lot of sense to have multiple shards. But now, just 8 months later, we're actually seeing a lot of growing demand on the network, and to the point where we think that it is absolutely necessary that we have more than one shard to accommodate for the ever-growing needs from the developers and the community. So how this is going to be done is that essentially we're going to take like a multi-staged approach where in the first stage we upgrade to simple Nightshade, meaning that there will be like 8 shards. And there will be separate chunk producers, but all the block producers would track every shard. And then later on, once challenges and dynamic resharding are implemented, we will actually upgrade to the full Nightshade that's spec'd out in the white paper. The problem is that challenges and also dynamic resharding, each on their own, requires a lot of effort to implement. Yeah, I will not actually talk in details about what those things are and why it's hard to build them, because that on itself would take a very long time to explain. So another thing that we're working on is to increase number of validators on the network. So today we only have 60, which is like a relatively small number compared to some other chains like Polkadot, Solana, and so on. So yeah, so we're trying to increase that by well, there are multiple things we're working on. For example, we're working on once we transition to simple Nightshade, I think there will be a lot more validators who are also chunk producers. And at the same time, we're also thinking about ways to increase the number of block producers on mainnet. So yeah, that's kind of the stuff that we're working on. Okay, let's move on to Runtime. So as I talked about before, the Runtime is an execution engine that's responsible for state transitions. So a very very naive or like very simplistic view of runtime, essentially you can think of this black box that you feed it with the current state, and then you give it the current block, and then it will return you the state after applying the block. So yeah, that's kind of a simplistic view of how it works. And actually underneath, or rather inside that black box, there's a lot of stuff going on to actually make it work. So let's just kind of briefly walk through an example. Let's say there's transaction it's from Alice to Bob, meaning that Alice is the sender, Bob is the receiver. So how it works is that the transaction, or no matter what kind of transaction it is, whether it's transfer function call or whatever, will be first sent to Alice shard to be processed. It will charge the transaction fees from Alice account that's necessary to convert it into a receipt. And after that, the receipt is sent to Bob's shard to be executed further. And then that receipt, of course, can create other receipts that go to maybe some other shard. So, and that process just goes on. So as you can see here, the execution is not synchronous, like synchronous execution, meaning that in Ethereum, a transaction would just be executed in one block and it would just be done. Here, a transaction execution can actually take multiple hops. So since we are a developer platform, I want to just talk a bit about how the contract execution works. So overall, like the developers would write some contracts, and then in a language that we support, and then they would compile the contracts to WebAssembly binaries in whichever in the compiler of whichever language they write in, and then they would send essentially a deploy contract transaction to deploy the contract to some account, and then so we're actually so yeah, it will be the case that the contract is compiled when it is deployed to some VM module, and then when the function call is invoked, a transaction that essentially means that they send a transaction to the network to call some method on the contract, and then the runtime would take that in, and it would start the VM to actually run the WebAssembly code. Yeah, that's a very brief overview of how it works. Yeah, so some of the challenges and future work on runtime. So first of all, the stability and the robustness of runtime is very important, because it's in a sense more important than other components, because runtime is responsible for state transition. And once there's a problem in state transition, it will cause the network to diverge. And it would not only cause that, but in the future when we have challenges, it essentially will cause the network to split into different parts, and then each part will try to challenge each other because they think the other part is doing an invalid state transition. And then when that happens, it just becomes a complete mess, and the state would just be very messed up. And then we have to, it's very hard for that to recover because essentially then we need to do some kind of hard fork to change the state, which is not easy to do. And things like this actually do happen, right? So for people who are following more closely with the development cycle, we recently found some bug in Wasmer, for example, that would cause this kind of behavior. So yeah, it's very important that we work on the stability, improving the stability and robustness of runtime. And we're also some other things that we'll be working on, including like figuring out better ways to charge for transactions. This means that we want to estimate better the cost of different operations, and also optimize some of the operations, including like host functions like storage read and storage write. And also we're working on better ways to price the gas price of the network, and addressing some developer concerns around gas and storage. I mean, today it is all confusing because gas is not something that people just intuitively understand, and also storage cost is high, and also today developers have to use some storage management standard to manage their storage when there is some method in their contract that allows users to increase the contract storage. So yeah, there's like a lot of work that needs to be done to improve the developer experience there. Okay, so finally, I just want to mention briefly about node experience. because this is essentially a kind of horizontal thing, meaning that it cross paths with all the components that I mentioned before. Essentially, here we want to make the experience of running near nodes better. So some of the kind of feature requests and the performance improvements that we're working on, including things like, for example, validator wants to have a longer time between when the protocol upgrade is voted and when the protocol actually switches to the new version. And also things like separation of different types of nodes. Today, they all use the same binary. They all write essentially the same kind of data to the same database, but that's actually essentially a waste of validator storage in a lot of cases that they don't actually, they're storing some kind of data that they don't actually need to store. And also we will be working on further optimizing CPU and memory consumption of near nodes. I think today, the CPU usage is mostly good. I think there's still some issue with memory consumption. And also we'll be working on testing of the stability of the near nodes through more integration tests and larger scale tests. So yeah, I think that's all what I wanted to present. I think, yeah, also it's almost exactly 30 minutes. Yeah, I think we still have a time left to answer some questions, right, Cindy?
Yes, you have 10 minutes, 15 minutes.
Okay, yeah, thanks. Yeah, any questions about the, yeah, Austin?
Yeah, I just had one question about you mentioned in the presentation and then also in that the governance post that you wanted to increase the amount of validators. Is that a protocol or technical change, or is that just onboarding more validators to get them on the network?
Yeah, so it's kind of both, but today we're bottlenecked on the protocol side that there is a hard requirement, the hard restriction that there can be at most 100 validators in the network. And also because of how the validator selection algorithm works, it's actually very difficult to reach that maximum amount because essentially the uneven distribution of stake would lead to some validator not being able to get a seat. And as a result, we kind of plateaued at around 60 validators.
All right, gotcha. Thanks.
Yeah, anyone else has questions or something I can explain better? I don't think I explained anything very well.
Oh, actually, I was about to ask whether we can post it on YouTube. We can share it. Would love to have such material, which goes on like overview and high level for the community. And I find the talk pretty well defined in this specific area of like going through everything in just half an hour.
Yeah, thanks for that. Yeah.
Can you also double check the participants if we're waiting for somebody?
I don't think there. No, I don't think there's anyone in the waiting room. Or
can you disable waiting room? Just
disable waiting room. How do I disable waiting room? Yeah, I didn't find how to do that. Oh, okay. Okay, disable the waiting room.
Yeah. Thanks.
So I guess if nobody has any questions, we can make a break.